Hello, welcome back to more Haskell live coding. It's been a couple of weeks. It's been a very busy couple of weeks work-wise, so I've kind of forgotten how to write code and, well, basically everything, I guess. I don't necessarily have the headspace for this either, but we'll give it a go, see how it goes. If all the coding is terrible, it's obviously because I'm busy and not because I'm crap at coding. Just a coincidence. I'm going to try and pick up where I left off last time. So we have virtual machine, and I was trying to implement call and return, and it didn't work properly. And then in the last episode, I implemented something to do some debugging, some tracing on the VM so it can print out every step that it tries to evaluate. And I also kind of quickly rewrote the stack as well. So I had gone from using a simple list to using a sequence, and then last time I switched back to using a list again. Given that the original aim of this was to learn how to write a stack machine, I feel like I'm not paying enough attention to the stack. So maybe where I want to start today is to move the stack out to its own abstraction, so that the VM functions are not so tightly coupled to the decision I've made about the data structure behind it, but rather to sort of abstract that away and provide some functions which do stack things like pushing and popping, but also maybe, applying a binary operator where we pop a couple of things, apply the operator and push it back on again. And then also things about jumping around in the stack. So in particular, jumping back, I guess. So for return, we want to jump back to previous point in the stack. So I'm going to try and focus on writing that well. And then hopefully I can then fold into the VM. And I'm hoping that just makes the problem with call and return go away. But if it doesn't, at least I'll be in a better position to understand what the stack is doing, whether or not it works. And then we can use the tracing to try and debug exactly what's going wrong. Okay then. So this is the code I had last time. Well, this is the test I had that's failing. So we have this function where we push two things on the stack and multiply them, so that should be 6. And then we call position 9, which I think is here. And then it should push 1 and 2 onto the stack and add them, so that should be 3. And then return should take us back to here. The return value should be pushed onto the stack, so we should now have 6 on the stack, but in front of it we should have 3, and then we call add, and then that should give us 9. And that's what it should be doing. Might draw that. So we have, what's our stack? So our stack initially is going to be 2, and then we're going to push 3 on, so it will be 3, 2. And then we jump forward to the function. So then we multiply first, sorry. So multiplication will turn it into 6. Then we call our function, so that's going to push 1 onto the stack. And then we push 2 onto the stack, which then with 2, 1, 6. Then we add, which should give us 3 and then 6. And then we return, and then we call add, which should give us 9. So that's what it should be doing. Right. But when I run it, it doesn't work, and it says, should be 9, we've got 3. 3 was the last thing on the stack from adding numbers together. So something is going wrong along the way. Okay, so in the VM itself, the stuff I was doing last time, apart from adding the debugging or the tracing, whatever, was I changed it. That's right. So the stack inside the CPU, here is a list of ints, and previously it was a sequence of ints. I did add a couple of helpers for pushing and popping, but then I had to walk through the whole code and update the way we use the stack. So what I might do, if I bring up the compile file, is just add another, or in the library, I might add another file to here called stack. And in the tests, I'm going to stack spec. And then we'll just write out what we think the stack should do. VM stack. Okay, so from here, I create stack spec.hs, and I'm going to pull this stuff in. Let's pull an example as well. Paste it in there. This is not going to be VM spec, it's going to be stack spec. We're not going to import VM, we're going to import stack. Oops. Don't think that needs to be qualified. And I guess we can write test saying something like it pushes elements onto the front. And then I want to say something like let stack equal empty. Don't know, I wonder about this. Like, should I make the stack a monoid, an empty stack, and then we can have operations on the stack which return new stacks? Let's not go there yet. Let's just start with something simpler. So we can say we're going to push the value that we're going to push onto the stack. So we'll say something like empty stack. The value 1, and then we will pop it. Well, that's not much of a test, is it? So we want to let's push a couple of things on. So we can say I might switch order around here. So let's push 2 onto the stack. We'll get to return a new stack. So we take this argument first, it makes it slightly easier to write. In fact, let's not pop it yet. So we're just going to build it up. And what we can then say is popping the stack should be 2. Something like that. So what this is testing is we push a couple of things on, pop it, we get the last thing we pushed onto there. Okay, let's go to here, create a new file here called stack. Yes, I want that. We're going to export. Well, we'll work out export in a second. I guess we want push, which takes a value. And returns, and the stack. And returns a new stack. Do we want to make it generic? Let's see why not. Let me just undefine it for a second. So we could just say something like new type stack is stack list of A. So here we can destructure this a little bit. We can say it's a stack of S. Need bracket from that. Stack int of stack A of S. That's hard. Let me just make a stack a list of ints. We can worry about making generic if we need to. So let me say stack s. Okay, and we can just return a new stack of b on the start of s. Wrong number of colons. Okay, we're taking a. We're going to take an int. That was push, and then we had pop as well, which goes from stack. Oh, interestingly, this goes to the remaining stack and an int, I think. So pop s, right, two cases here. So popping a stack that's empty is tricky. Let's go undefined, but popping a stack which consists of an x of anything, I call it v above, let's call them all x. And then this can be anything that's left. That's going to be x, and then a new stack consisting of x's. Okay, so I don't know what to do in the empty case. I mean, one way of doing this would be saying maybe an int. It's going to make my life difficult. We can also say either that, and we just make it a string, I guess. So we could say, in this case, it's left, popping empty stack, and in this case, it'd be right. So we pop, oh, not back to there, we pop back to the stack spec. This, oh, I need to export some stuff. Okay. Let's export stack push and pop, and then we needed empty stack as well, didn't we? So we can say empty stack. So I could make a monoid, but I don't think a semigroup implementation makes much sense. Like, you're not going to take two stacks and join together. You're going to take a stack and just push onto it or pop from it. So let's just say empty stack is a type stack. An empty stack is just stack of the empty list. And then export it as well. Okay, back to here. So now we have a problem. So when we pop, it should be right 2, and then a stack with just 1 inside it. Okay, does that work? No. No instant first show stack. Can we not? So it derives that anyway, but anyway. Deriving show equal. Try that again. Okay, so one failure, but it's still a VM failure. What could we do? So we could say it returns an error when popping an empty stack. And then we can say pop of empty stack. This should be left, and then what was the error? Some error. Don't know what that is. Can I match like that? No, I cannot. Okay. I could put the actual error message in, I guess. Guessing that will still work. Yeah, one failure, it's not my failure. Okay. Let me just move this into some blocks, so indenting by 2 spaces. And we can say describe function pop. And grab those and indent them. And then here we can say describe bin op. So we could say it applies the operator to the top 2 elements and produces the result. Good description, nice and catchy. So we'll set this up again, and then we can say bin op. We'll use plus. We'll use our stack. And then this should be a new stack. So it should be stack 3. Okay. This won't work because I haven't defined bin up yet. Oh, but it also doesn't work because I haven't imported describe. I don't know why this is not working. I would expect it to warn me about that. Maybe HLS is not happy. Okay, cool. So now we get problem with bin op. We jump into here. We can export bin op. And we can say bin op goes from stack. No, goes from. The minute has to be int to int. That's our operator. I'm going to take a stack and return a new stack. So bin op. Then we have a stack with x, y, and then I guess z's, z's. Right, so this is going to be either a string or a stack. So these things we can say it's going to be right of a stack with the result pushed onto z's. Stop taking spaces for. I need to to work out how to configure this properly. Where result, that's just x op y. Well, I need to sort these around because of subtraction. I couldn't expect to type int to t with actual type int. The function op is applied to oh yes, of course. Type checker is right, obviously, and I'm wrong. So we take 2 ints and we return an int. Okay. Then we can say bin op of anything else is left not enough elements on the stack. Okay. Okay, so it's an either stack now, and I'm comparing it to stack. So this should be right of stack 3. And then something like it. Might as well write this case 1 here. It returns an error when there are not enough. Actually, returns an error and there is 1 element on the stack. So we'll just create a stack with 1 element in it. So this should now be left not enough elements on the stack. And then we can do the same thing again. It returns an error when there are no elements. So here we can just use empty stack. Does that work? 20 examples, 1 failure. Cool, okay. So then what can we do? Next thing I want is this return function, I think. We might as well call it return. So what are we going to do here? It does 2 things. So it puts the top of the stack onto the combination of things. So it takes the top of the stack, drops the unwanted elements, does that, drops them with balance, and then produces the return value. Quite a lot going on there. So start with a stack. Need quite a few of these, so let's go. Can we use a fold for this? we left fold this thing? I think we do. We start with an empty stack. Then we're going to push 1, 2, 3, 4. We need another argument to this, which is push. I think that's what I want. I'll just check that. It should be, push is always safe, so it should be a stack containing 4, 3, 2, and then 1. It's a stack, the reverse order. Just check that works. It is not. Do I need to bracket that? No, that wasn't it. Couldn't much expect to have int with actual type stack. Expect to type int with actual type stack, so it thinks that stack here, if I can get it, is an int. What's the function I'm looking for? So we're going to start with let's try to bring up a new terminal, GHCI. So what's the type of foldle? Other way around. So take initial value, our list, and we get back that thing. Okay, does that fix my problem? Nope. Just use non-strict foldable. Didn't make any difference. Ooh. Not in scope. What's the type of fold from Prelude? Foldable and monarch? Nope. Not in scope. This thing. So B to A to B, because we have a list of ints and something type B, and B in this case is a stack, and it wants a function which goes from stack to int to stack, and push actually goes from int to stack, so I need to flip these arguments around. So let's see if flip does the trick. It does not. Okay, what's the type of flip push? Type of flip push is stack int stack. So now we should, oh, foldable, sorry. There we go. Okay, that did work. Right, bit of a kerfuffle, but I can now helpfully create a stack. Let me just create a helper for that. So make stack takes a list event and returns a stack. Definition this was fold of flip push on the empty stack. So here we should be able to say new stack. Good, that still works. Okay, right. And then all of these can just become mixed stack as well, I guess. That was 2 and 1, but actually so it rounds to 1 and 2. This is mixed stack of 1 and 2. That could be a mixed stack of 1, but there's not really much point in that. Right, just make sure I haven't broken anything. Okay, 1 failure, that's what we want. Okay, this is more interesting. So we got 1, 2, 3, 4. But our stack ends up like this. What I want to do is take 4, maybe jump back to here. Now let me put more stuff in. Why not, eh? So we're gonna have, oops. What have we got? We've got, let me put it back in, we have 6 and then 5. Okay, I want to take the top one, which is 6. Then I want to return to position 3, for example. Let's go even further. Let's return to position 2. That's okay. So if I say something like return to stack, return is not a good name. Let's call it ret. So we should get an error because we haven't defined ret. Okay. So back in here, we can define that. I'm going to do something like return. So it's going to take an int and a stack, and it's going to give a stack. So return is, let's change that. Return is, so that's the position we're going to and some stack. This is a new stack with the old heads return value. And when we do that, we're going to push it onto the list of the truncated stack. We should probably do some checking as well. Actually, this might return either string or stack. Okay, where? Actually, I might use guard for these. So we can say where the length of S is less than P. So we want to jump to position 2, but we've only got one element in the list. This should be left jump outside stack, something like that. Return to invalid stack position. And then there'll be some other cases, but let's just work through this. So otherwise, we return right of this stack where return value so we need at least one thing in the stack. So we need a stack with an X and then some X's, I guess. So return value is X. So we need to put that in there. I'm just going to flip these conditions around a bit so we can say length of S, oops, it's greater than P. So I don't know if I can put where in the middle of a guard. Let's find out. Truncated stack is drop PS. No, I don't think I can, but I could just align that. Okay, and then we can say return of anything, and anything is left. No elements in stack. We don't drop the X, we drop of X's. And do we drop P? No, we don't. Okay, so we drop the difference between them. So if our stack is of length 6 and we want to go to position 2, we need to drop 4. Let me capture that because that's kind of important as well. So the length of S is that thing we do drop from there. We don't actually capture X's. Right. So where truncated stack is drop difference from S, and the difference is the length of S minus P. This is truncated stack. Okay, does that work? Probably not. I can't match it because I've changed the type, so this should be right of that. Cool, that works for some reason. So it returns an error when the stack is too small. You can say stack is 1, 2, 3. Oh no, okay. So I would say this is actually when it's too high. So this is going to be like 7. We can't jump to 7 because there aren't 7 elements in there. So should be left and something like not enough elements in stack. Can't remember what it was. Not enough elements in stack. No, it's return to invalid stack position. To invalid stack position. Okay, and then it returns an error when the stack is empty. So you could say return 0. Actually, if you said return 1 of an empty stack, it would get picked up by this. So the stack generally is empty. The fact we can't pop it doesn't really matter, so you can't return anywhere. So I'm tempted to say this should be right of empty stack. So if your stack is empty and you try to return to 0, it's not actually a problem, I don't think. But that'd be a nonsense thing to do, so let's not support it. What's the message here? No elements in stack. So these strings, no elements on the stack. And it kind of lines up with the one above. But run it. It should say should be. Okay, well, a lovely abstraction. Can I now use this in my VM? Import stack as S. So CPU stack is going to be stack. It's going to be s.stack. Okay. Well, this is what I was tracking the length and stuff, but let's get rid of that. Let me get rid of these for a second. I might add something similar back in a second. Okay. So shouldn't really allow me to do this. Empty stack. What was the result? Is popping the first thing off. Okay. So We can just say show pop s. I think we'll have to do something similar in here, I guess. Yep. So empty stack. And this is show pop s. It's not going to be super pretty because it's going to be left or right in this case. So it's going to be right something. And in fact, we don't need that anymore because pop now returns the either type. Okay. So, go back to step call in a second. We'll come back to these later. Step op. So we don't need to do this popping stuff anymore. Because this was horrible. It's just going to be CPU where what do we do in here? So CPU IP is CPU IP plus 1. Are we going to advance by 1? Something else must be advancing already. No, it's not advancing already. Oh, that's right, sorry. The operation is only 1 byte long. So it's going to be add or multiply, whatever. And then the CPU stack is bin op CPU stack, which we need to capture here. We should get rid of all that stuff. I guess it's all right. Can we format this better? Not sure it's better, but there we go. Okay, so we call it, we advance the ID, and then we set the stack to be whatever bin op is. Okay, call. Right, we might need a new function here. So okay, let's do this. So we're going to try a new CPU, I think, and this is where the IP is the call address. That's okay. So the call address is the next instruction. And the stack the stack is unmodified, but we set the stack pointer to be where we were called from. Is that right? Yeah. Yeah, ish. We also need to put the return address somewhere. There are a couple of things going on here. See if I can get this right. So we have instructions, so it might be something like 1, 2, we can multiply them. Then we can say call, and then whatever the address is, I think it was 9, something like that. And then we add them together, and then we halt. And then we have the definition of the function, which is something like 1 to add and then return. I think it was something like that. And then our stack at the point at which we call it, so like at this point, the stack is just going to be, I guess, 2, because that's a multiplication. And so inside our CPU, this is our instruction pointer, and it's going to be 4. Our return address is going to be 6. The return address we need to store somewhere. I can't remember where we store this. The other thing is our stack pointer will be here. Okay, so what I might then do, and what I think I was trying to do before, is that we're actually going to do a little bit of extra stuff here. So what we will do is we will take the return address and we'll put it onto the stack. Okay. Stack pointer doesn't really make sense. It's not exactly stack pointer, it's stack length. However, we still want it, we kind of want it to point here, and then all of this stuff, right to wherever the stack finishes, is our stack frame. And the first thing that we push on the stack frame is the return address. But then when we start to execute the functions inside here, let me just grab another color. Does orangey kind of work? Actually, let's try and go reddish. Hope this works okay color-wise. So, oops. It's picking up my hand. This is where we start our stack frame. So we push 6 onto it. We will push 1 and 2 onto it. And then we call add. So that's a bin op. So what that's going to do is pop us off and put 3 back on. Stack pointer is still 1 instantly. Then we hit return. So return is going to find that the stack pointer is 1. It's going to pop this. This is our return value. What we actually want to do is not go back to 1, but go back to 2. Right, so what I want to do is say, jump to here, pop this off. This is our new return address. In that case, actually, it's going to be slightly simpler. If I move the stack pointer to here, so we update this to be 2. So at the point at which we call, we're going to push the return address on, update the stack pointer to reflect that, do all of our work. Then when we call return, we're going to pop the thing off the front. We're going to jump back to 2 in this case. Then we call pop, and then we will push the return value onto the stack. Okay, let's give that a go. So what do we say here? So for call, what we want to do is the CPU stack pointer. I mean, we can put this in there. Very well, it's fine. And then this CPU stack is pushing the return address onto the stack. Okay, so we have return address, so we have CPU stack we need to capture here. Okay, so the new stack pointer is the length. It's actually going to be length of new stack. A new stack is where we're going to push the return address. We push return address onto the CPU stack. And the return address is this integer. So we go to the next instruction. We go to the next instruction and we, what do we do here? Go to the next byte, sorry. And we turn it back in an integer. Okay, that's cool. So the C, oh no, sorry, no, that was wrong. This is the call address. So that will tell us where we're jumping to. What we're interested in is where we're jumping back to. So return address is CPU IP plus 2. So wherever we are now, and then the next instruction is the address we're jumping to, and then the next instruction is the place we're going to come back to. Okay, and then we can do this. And this is s.push that. Okay. The length of the new stack. I could we could add a new thing here, so we could say s dot position. We'll hide the fact we're using length. Okay, let me quickly jump to here. This should be really easy to write. So position takes the stack and returns an int. Position of stack of s is the length of s. Then we'll export this as well. Okay. So that's call. Return. So what I said this was going to do. So we already have ret inside s. So if we call s.ret, it's going to give us back two things. It's going to give us back the result and the new stack. This is called s prime or stack prime. So this is brings off a minute. Might be difficult with the red behind it. Go open that for a second. So the thing that gets returned is the value 3, and then separately this stuff. Okay, so we have the result and we have the new stack. S.ret gets applied to CPU stack, but it needs another thing. It needs to know where to jump to. So this is CPU SP. Okay, we need to deal with the error as well. So I'll come back to it in a sec. Let's work through the logic. So we have the result, we have the new stack. The next thing let's do is say the return address is popping of s.ret. No, sorry. We pop stack prime, it's s.pop. And then we can say new stack is the result pushed onto this, not quite that. And we call pop. It's going to give us the return address and stack prime prime. And then we do that. Okay, which is kind of okay, but it's going to break down because all of these things are ethers. So can we write these as series of little steps? And then I think, let me just test something quickly. I think if you say something like A is write 1, B is write 2, C is left error, and D is write 3. So if we have some kind of either type, that's because we've got A, and then we feed it through a function which is going to take actually, let's do something like add either. Now let's do add. What I'm trying to work out is can I like fold over, or can I map over a list of ethers or a sequence of ethers? And only apply it if it's the right, and as soon as we hit left, then we get another left back and we stop. Right, so we look at the implementation of fmap. So we say fmap, let's say +2 of A. Ooh. What's that going to do? So it's going to go some kind of number to either A, B. Okay, A is an integer in this case. If I just show that, no. Do we know what A is? does it help if I say this is of type either string int sake. So the type of a prime, either string int, okay. So now can we say fmap plus 2 over a prime? Hit right 3, okay. So if I take my C, left error of type either string or int, and then fmap, oops, plus 2 over C prime, you get left error. That's okay, that's what we want, I think. So is there a way of sequencing these things together? What I'm wondering. Why do I want to sequence together? Because we don't know whether or not the previous one returns an error. So we have if we have something of this type, so f in this case will be the either type. So we want a function which goes hang on. What I'm hoping is we can start with an either some kind of int, the left int, sorry, right int. Then we can go from int to int. We get this though. Is it something like so you can say add maybe add 2. We just partial apply plus 2 here. But we're going to say this is of type int to int. Well, I'm not sure this is right. Because what I'm thinking is, can we say add 2 and then apply it to a prime, and then take the result of that and apply it to C prime? No. Is it just that again? No. For all these kind of things we can use. Ooh, that's the one I wanted. Okay, and then if we apply it to a prime again, you get left error. Right. Okay. Does this make any sense? If I get rid of those, sorry, let's apply it to a prime twice. So if I did if I have a prime and I apply it to a prime again, you get this value, and then C prime, you get C back, and then a prime again. Left error. Okay. I think I'm getting there. So what we could have is something which does let's call it ret, and it's going to go from a CPU stack to either string or a stack. And then you say ret, let's use s.ret of CPUSP CPU stack. Let's go back to that for a second. I don't really need these functions, I'm just trying to think it through. So we take that, which we know is one of these things, and then we can say something like return address. It's going to take an either no, it's going to take a pair of result. So result is going to be an int in this case, and a stack. Oops, it's an s.stack. And it's going to return something of either string or an s.stack. Then we can say return address and it's given some some address and some stack, and that's just s.pop wait a second. It's tricky because when we're trying to get tuple, I want to grab this result out of it each step of the way. Do you know what? I'm just going to give up and you do. Oh, am I? No, I'm not going to give up yet. So given this, we're either going to return a result, which is an int, or a stack. Okay, so we pop do we want to? Yeah, we do want to get to return address. So the thing we're going to return from here, it's going to take a result on the stack. So the output from this, and it's going to pop the stack and this is the thing that can return an either type. So the result of popping the stack is return address and a new stack. And we want to, it's difficult because we're going to hang on to the result. So it's getting too tricky. Right, start again. So s.ret I should delete that. It's undeleted. Right. So you can say let result stack prime come from s.ret CPU sp CPU stack. Don't need a let in this case. Don't think you can do this. Okay. I want to avoid the nested cases and anything, so you can say something like case that of left error is CPU with CPU error. Is that? We actually get rid of the do now. And then right error is now case it's not right error, sorry, it's right result and some stack is case s.pop and then here we can say if we fail to pop then return the CPU error. And write the return address and the even newer stack. And then we're good to return. Then we return a CPU with these things. So CPU with we set instruction point to return address. We set the stack to be s prime, and it's not quite s prime, it's s dot push to result onto s prime. We're only holding for debug reasons. And that's it. Okay, couldn't match type list characters with maybe string. Oh, it's just that. And it's just that. Okay. Now what happens? Pop should give us a pair. Should it not? Oh, sorry, return. What did return give us? Take an int in the stack. Int always return to some point. No, okay. We take a stack and a place return to, and it doesn't give us anything. So it just gives us back S. Okay, so we need to get results back. So we can say case s.pop of CPU stack. So if we get an error from that, and if we get a result and an S, it's so nasty. Then this becomes S prime, and this becomes S prime prime. And then we use it down here. I'm going to use this as worrying. Okay, so first of all, we pop it, deal with the error. If we didn't have an error, then we have a result and the remaining stack. Okay, so now here we use that S. If we got an error, we return the error. Otherwise, if we didn't, we have a new stack. Then we pop it. Got an error, we return it. Otherwise, we will have a return address and an even newer stack. Then we use the return address, new IP, and then we push the result that we got at the very beginning onto the remaining stack. Really horrible. Binet might return an error as well. Of course it might. Okay. So here we can say case bin up. And then of left error is CPU, but the error is just error, and then right of the new stack is this, and CPU stack is S. Okay, so it's going to work well, but anyway, we have colon return, and then this push thing. What have we got here? So we got an IP, right? We're going to create a new CPU where CPU IP is equal to CPU IP plus 2 because it takes that extra argument. So the next byte is the value that we're pushing, and then the stack s.push a new value onto the CPU stack. V is from integral that from grill of that. Okay, obviously this works perfectly fine. So this is s.empty stack, s.pop, s.pop. The rest of that seems okay, I guess. Have we got a VM spec that's all broken? Not necessarily. Let's just try this. Ooh, not that. Does it even compile? Compiles but runs forever. Okay, bin that. Do that. Okay, what time is it? 26 minutes past. I've gone on a bit too long. I'll come back to this next week. So pushing and popping is still broken, but we do have an abstraction around the stack. I need to work out how to do this in a nicer way, and I need to work out why it's not working, but we can trace for that. Cool. Okay, thanks for watching along. Yeah, next week we'll pick this up again, and I'll see if I can make it actually work this time. Cool. Hopefully see you next week. Goodbye.